family for being here. Welcome to, I call it the People's Republic of Cambridge. And it's always fun around here. Where do I begin? Take a long time. But so,
I mean, I have taken quite a while.
Okay. Alex came right after he finished for University of Pittsburgh. And initially he thought he wanted to work on carbon nanotubes and experimental stuff. But they said, okay, let's look at a little bit of modeling. And the more he dug into it, the more he wanted to look at. And he got into the physics. Even though his physics was still coming here, but he went to the physics department, took a lot of classes in classical mechanics, statistical mechanics, and it really became really versatile with all the classical and quantum mechanics that you commented. So then, research-wise, he decided to attack really the problems that existed, but everybody has kind of skated over and said, okay, let's leave it behind. We'll just think about things as they look and use them. But he dug deep into them and really reformulated something that everybody has just kind of left alone. And I was really pleased when one of the reviewers came back and said, geez, this could be really heartbreaking. And the reviewer essentially came back and they said, wanted us at that point to help him do some things. So with that, I shouldn't go too deeper than that, but just to say that it's been a pleasure to have Alex on this. Working with him, the more we went into it, it was like we were working as colleagues. And it was always nice discussion at any time we got together. And he took me in directions that some I would normally would not have gone. Take me in that direction. So,
Alex, thank you, Tyler. Thanks for giving context to the presentation as well. Not have to introduce it as much, but thank you for being here. And I will talk about the main points of my thesis work, which was reformulating theory and modeling field electron emission, and then using this reformulation to derive models for low-dimensional emitters, which correspond with what people are making today. The first question to be answered is, what are field electron emitters? And foremost, they're cold electron sources, as opposed to hot electron sources, which I'll discuss later. And physically, they're sharp tips on the nanoscale these days, and they emit electrons under an applied electric field, and they're usually fabricated in very large arrays to increase the density of these tips for higher current output and smaller footprint. And over the years, they've been used for a varying range of things, and this phenomenon has been known for a long time, but hasn't found major commercial uses outside of electron sources for different types of microscopes and spectroscopes. It was in the running to replace CRTs in the late 90s and early 2000s for the next consumer flat panel display technology, but was beaten out by LCD screens due to mostly reliability issues. And the current pushes are mostly in large arrays of these emitters, and in imaging, they're being used for radiation generation, terahertz microwave and X-ray. And there is also a push to use them for multiple electron beam lithography. And the advantages of these are people are trying to fabricate large arrays of them and then have each of the tips be individually addressable temporally and spatially as to control them individually. So you can do lots of things in parallel. And the one on the bottom, which I'll talk a little bit about in the context of my own research, is vacuum nanotransistors. And in vacuum nanotransistors, the channel, which is typically silicon or semiconductor, is replaced by vacuum, or ideally by air, if the channel length is smaller than that of the mean free path of electrons in air. And basically, this eliminates any kind of scattering collision between the channel theoretically accelerated to the speed of light. So this is for higher power and faster switching devices. So how do field electron emitters work? Normally, in the simplest model, electrons are held inside of the material by some sort of potential barrier, and that, depending on the material, it's just the amount of electron or the amount of energy that's required to pull an electron out of this material. And in the case of field emitters, no current flows in this case. And I mentioned hot electron sources earlier. The traditional way to get electrons out is to heat them so they go over this barrier. And this can range from 5 to 10 electron volts, and typically this requires the cathode to be heated to about 800 to 1,000 degrees Celsius. In field electron emission, however, if you apply an electrostatic field, it bends its barrier down and gives the electrons a finite width to tunnel through the barrier quantum mechanically. And if they're able to do that, then the electrons come out. And cold in this case means it can be done at room temperature. And this is the basic process behind how field electron emitters work. This was observed for a long time, but it wasn't able to be formulated physically or mathematically until the advent of quantum mechanics in the 1920s. And with the new theories of semi-classical tunneling, Fowler and Nordheim were able to derive the first equation for field emission, which has this simple form. And it describes emission from a bulk planar metal emitter at 0 degrees Kelvin. And so the bulk part means that it's not quantum confined. All the electron energies are continuous, and planar means that it's flat, and the metal just simply means that it's metal. And the simple form is what's mostly appealing about this. They were able to capture the basic physics of electron emission. And really, there's only two things that are significant in this. It's the height of this barrier that keeps electrons in for function, and the applied field of the surface that bends down the barrier. So I want to take a moment to discuss why those three assumptions were made in deriving the Fowler-Nordheim equation. And they both come from technological considerations at the time, but also it makes the math easier. So back then, they weren't considering artificial nanoscale systems. They were considering natural nanoscale systems like molecules and atoms. And for all intents and purposes, energies in these devices were following classical rules. So they were continuous energies. Planar, simply because it's the easiest way to do the math. In a planar emitter, the electrostatics are one dimension, so you only need to worry about variation of the potential along one coordinate axis. And finally, metals, for two reasons. That's what they were using. People weren't really using semiconductors to make devices at that point. They were still investigating the theory of conductivity and then later semiconductivity. But also, it also makes the math easier since it's a perfect conductor. It has enough electrons to screen an electric field at the surface, and it separates the electrostatics calculations inside the emitter from outside. And at the center of all these approximations or assumptions is the Fowler-Nordheim equation, which ends up being mathematically the simplest way to describe field emission. However, if we look at the modern emitters, first of all, they're not necessarily or usually even made out of metals anymore for reasons I'll discuss a little bit later in the presentation. For example, this tip, which was from a former group member, is made out of silicon. The assumption of a bulk emitter is also broken for modern field emitters, and I've outlined this particular diameter here as 10 nanometers. Quantum confinement effects need to be considered when the wavelength of the electron, which, for example, can be about 5 nanometers, is on the same order of magnitude as the quantum well to which it's confined. In this case, is the emitter diameter. And since emission happens from the end of the tip, anything above here reasonably shouldn't be treated with classical or bulk electron kinematics. And for the assumption of planarity, even when Fowler-Nordheim derived their equation, these emitters weren't planar. This is especially the case now. The paper that this was published as a part of after the thesis was billing this as atomically sharp tips, and this radius of curvature of 1 nanometer is about a couple of atoms. So the Fowler-Nordheim equation doesn't look too good today, and this is not specific to that particular type of emitter. With the advent of nanomaterials such as graphene and carbon nanotubes, they've been made out of a variety of materials that are non-metallic. They're still made out of metals, but the tip geometries are not planar, and in this case, these are silicon ones. So it's clear that the Fallon-Nordheim equation out of the box doesn't necessarily work. And it's been known for a very long time that the Fallon-Nordheim equation, while a good qualitative model, doesn't actually help predict how much current is automatically emitted. So over the years, people have really tried to stick to Fallon-Nordheim because it's the central equation of the field, and they've done all sorts of acrobatics to include these sort of perturbation corrections to the field emission model to try to account for things such as temperature, band structure variations, different tunneling barriers, different treatments of tunneling at some classical limit. And it still doesn't really work. So overall, I think it's pretty clear that the Fallon-Nordheim model is just physically inadequate. It doesn't describe physics as they actually happen. And so the conclusion here is that we need to return to more fundamental physics of field emission and stop trying to twist and bend the Fallon-Nordheim equation and model into what we're looking for, and to look at specifically what types of emitters are we really trying to model and do emitter-specific models. And that's what has been done to an extent over the last probably 60 years. The first was done on semiconductor emission with the coming of the semiconductor industry in the 50s to the 70s, and simple models for emission from silicon and other semiconductors were derived over the course of a couple of decades. Next, as nanofabrication technology improved, people were fabricating sharper and sharper emitters, and it was becoming extremely clear that Fallon-Nordheim doesn't predict even the qualitative conclusions of the Fallon-Nordheim model. So there was a push to start developing Dawson-Mohanty did a multidimensional tunneling method as opposed to the Fallon-Nordheim, which is a one-dimensional tunneling method. And recently, Kiritzakis generalized the Fallon-Nordheim equation for emitters which are generally rounded. So it's meant just for rounded tips. And in the around 2010, Richard Forbes started working on kind of machinery that's needed to treat emission from low-dimensional systems, some tools that were needed to update Fallon-Nordheim to be able to deal with discrete states. And as a part of my master's work, I put together a general formulation of how to derive emitted current density equations and models from planar emitters, which are made out of metals, but are low-dimensional. But modern field emitters lie outside of all of these things. And it really seems like people only want to deal with one non-ideality from Fallon-Nordheim at a time. So in order to get out here, we need to throw off all of these kinds of approximations. And the real problem is, or maybe the solution is, that all of these field emission models come from some basic understanding of field emission in multi-dimensions. And in order to be able to unify these and also derive models for any place in this map, it's important to understand how field emission works fundamentally. And this was the main part of my thesis work, was to develop a physical framework based on semi-classical quantum mechanics that is able to describe field emission generally. And then if we want to derive models for any of these regions, it comes down to making a set of assumptions that leads you to these particular regimes. And so that's what I'll discuss first, is the basics behind field emission in multiple dimensions. I'll skip the majority of the math for everyone's benefit, but I'll try to give a diagrammatic understanding of how it works. And then from this, 3 new emitter models are derived using the framework as the basis for them. Okay, so the basic model of field emission is an anode or a gate that applies a voltage to a grounded emitter, and this voltage is what leads to the electrostatic field that bends down the barrier and allows electrons to tunnel. And inside a material, electrons have some amount of energy, and they are moving around, constantly hitting the surface of the emitter. And the number of electrons per unit area, per unit time, that are trying to tunnel, or at least hitting the surface, is known as the incident current density. When the electrostatic field is applied, there's a region in here known as the classically forbidden region, and this is the region through which electrons need to tunnel to get out. And at each point on the surface, electrons, depending on the potential, will take a different path to tunnel out, but they have a probability of tunneling called dq, the tunneling probability. And the electrons that make it out are the actual current density that comes out of it. the field emitters. And JQ is known as the local emitted current density because it changes as a function of position on the surface depending on how large A to Q is and what the tunneling probability is. This is as far as I'm going to go with the math, but I wanted to show that the incident current density is the product of the probability that the electron is in this particular state, given by the Fermi-Dirac distribution. The normal probability current density, so this just basically measures how many electrons are passing through a particular plane at any given time. And this plane that the electrons are being, the flux is being measured through is actually the emitter surface. The local emitted current density is a simple expression. It's the number of electrons trying to tunnel multiplied by the probability of them tunneling, which ranges from 0 to 1. And find the total emitted current, one has to integrate over the entire surface. So it turns the current density into a total current. And then sum over all contributions from states Q. And to get what is typically known as the emitted current density, simply emitted current density, divide the total current by some emitting surface area, which either can be the whole emitter surface or it can be some extracted effective area. And so that's all I'm going to say about the framework, but it enables us to derive models for pretty much anything we want in terms of emitters of any dimensionality, material, or geometry. And in this case, the first thing I'll look at is a low-dimensional, highly curved metal emitter. And to show where this lies on the map of field emission theory and models, it already throws off two of the assumptions of Fowler time. So looking at a metal still, but a low-dimensional, highly curved one. But before I want to get into it, the models are based upon two physical phenomena that are extremely important at the nanoscale. The first one is quantum confinement. And as I mentioned earlier, quantum confinement becomes significant or at least observable when the dimensions of the emitter are on the order of the electron wavelength. And this typically occurs, for example, around 10 nanometers or below. But in the bulk case, which is a case that is in line with classical mechanics, the electrons their states form a quasi-continuum, so the electron energy is continuous. And this corresponds to everyday life. For example, accelerating in a car from 10 miles per hour to 20, you go through 10, 11, 12, all the way through. Quantum mechanics, however, this is not the case. If the emitter is confined to a dimension that is, for example, 1 nanometer, the energy levels actually start to split and become discrete and are no longer continuous. And with this car analogy, that would be accelerating from 10 to 20. You don't go from 10 to 11 to 12, you just go from 10 to 20 and then to 30. So there are gaps in the available energy states between each of the subbands. So this is the major effect of quantum confinement in these models. And the consequence of this is that if there's a decrease in the number of states bringing in energy, that translates to a decrease in the spatial density of electrons. So what is expected as emitters get smaller, they can support fewer electrons, and that leads to fewer electrons able to tunnel for field emission. And the next thing I'd like to discuss is an electrostatics effect. On the left is a plot of the potential barrier outside of the emitter, where purple is the lowest potential and the reds are the highest. And if the electrostatic field is plotted, which is essentially the gradient of the potential, you see that the highest fields are concentrated at the area of highest curvature, and this is known as electrostatic field enhancement. And generally speaking, larger electrostatic fields congregate around highly curved surfaces, and this is just an effect of geometry. And the consequence of this is a higher electric field means that electrons have an easier time to tunnel out. So conventional wisdom, the field emission holds, is if I can make the electrons smaller, I can get a higher field for lower voltage, which means I'll get more current for a given voltage. So decreasing the size of the emitters traditionally increases the emitter current because of this higher field. So back to the model itself. Why a parabola? The major reason is because it looks like a real emitter. It's tapered and it's rounded at the emitter tip. And most importantly, from a physical point of view, it combines both of the previous effects that I discussed on equal footing. So both of these, the electrostatic field enhancement and quantum confinement, change with changing the emitter radius. And why this is important is usually one of these things is abstracted away and added later. They're not treated equally. So in my previous models for my master's degree, I would, for example, use something that wasn't curved at the tip, but it was a cylinder. And then I would use the electrostatic field enhancement factor of a shape like this. So you kind of impose one of the models onto each other. And a paraboloidal anode is for practicality reasons. It enables an analytical expression for the potential, which is needed for numerical tunneling calculations, or at least it makes it much easier. So this is the device structure. This is the emitter in here, and this is the anode. Usually about factor 14. What am I interested in with this model? The first question is, what's the dimensionality of the electron system? It seems like a strange shape because it's very small at the tip, but it gets larger as you move away from the apex. And so one would expect that at the bottom of the emitter, it's almost three-dimensional because the dimensions are 20 or 30 nanometers in terms of, this is larger than what's considered to be quantum confinement range. But at the tip, the radius of curvature is 1 nanometer. So does the dimensionality change, or is there a consistent dimensionality to it? Secondly, of these subbands that I expect to form based on quantum confinement, which ones emit the most and why? The large question technologically is, does the current continue to increase as the emitter dimensions decrease, which is the conventional approach I mentioned earlier. And as I mentioned, quantum confinement, we expect that the number of electrons available to tunnel decreases. But due to electrostatic field enhancement, the tunneling probability increases. So these competing effects, to see how they, which one wins at the nanoscale. And then lastly, Fowler-Nordheim plots are basically the tool that the Fowler-Nordheim equation is used for. What they do is they take experimental field emission data, plot it on a special set of axes, and if it's linear, people say it's field emission, and then they extract the slope, and you can extract things like the work function or the barrier height. And so what do these look like on nanoscale meters that have highly varied surfaces? First off, the dimensionality. I chose an emitter of 1.5 nanometers, and to measure or to determine the dimensionality, what I did, or what the standard procedure is each of, there's a quantum number that will correspond to each portion of the energy of an electron in a particular state. In this case, these three numbers are P and Q. It turns out that P is an integer, so not a continuous value, and it is due to the axial symmetry of the emitter and the boundary conditions that the wave function needs to be continuous on a circle. And N comes from the confinement to the actual paraboloid shape, also an integer. And Q is, it doesn't really have a name, but it does control the total energy. And so varying P, so these are electronic subbands with the emitter. This is the total energy, and this is varying Q. Varying P actually leads to a discrete jump in energy. So this is not considered to be a degree of freedom. Varying N also leads to a large jump in the energy levels. It's also not a degree of freedom. However, varying Q tends out to be a continuous value. Varying Q lets the line move up and down along each of these subbands. And this is a degree of freedom since it's continuous, so this is a one-dimensional system. As the emitter gets larger, it approaches a three-dimensional system because all of these subbands that have a spacing that is visible spacing, actually, they come together and they start to on top of each other, and then essentially the distance between the subbands, like you can see it's blue and green here, become negligible. And these values, P and Q, for very large emitter, become essentially continuous. So of these P subbands that I mentioned, which ones emit the most? And the answer is that all of the current, regardless of the emitter radius, comes from P equals 0 subbands. And this is an effective angular momentum. P actually corresponds to quanta of angular momentum, and it can range from 0 to any integer. And the kinetic energy associated with this angular momentum is given by this. And the major things to note are it's proportional to P squared, and it is inversely proportional to this parameter psi. And as psi increases from 0 to a larger value, it corresponds to moving away from the tip of the emitter towards the base. So psi equals 0 is actually the very tip of the emitter. Since this kinetic energy is moving parallel to the surface, it's essentially an electron orbiting in a circle, it's not available for tunneling. It's not moving in a direction that's useful for tunneling. So the available tunneling energy is the total energy of the state minus this kinetic energy due to angular momentum. And as I noted earlier, it's inversely proportional to psi, so as one approaches the apex of the emitter, the amount of tunneling energy rapidly decreases as this term increases. And what I show here is that for P not equal to 0 subbands, this lack of tunneling energy actually leads to a severe drop-off in the transmission or the tunneling probability through the barrier. So that across, this is the first 5 nanometers, as you can see here from the tip apex here on the side of the tip. As one approaches the tip, basically all of the other subbands with non-zero angular momentum experience a very significant decrease, and this leaves equal 0 subbands is really the only ones who have a significant chance of tunneling out. So the conclusion is that angular momentum, if a state has angular momentum, it will not be emitted. And the next thing I wanted to look at was this idea of scaling down the emitter. What happens as the emitter is made smaller? Does the current increase or decrease? And the first thing I wanted to see was, this is an artificial test, essentially. If I were to keep the transmission probability or the tunneling probability of electrons constant and decrease the emitter radius, what effects can I see on the emitter current density due to this effect of quantum confinement reducing the density of electrons that are available to tunnel? And as you can see, it decreases by a couple of orders of magnitude. And this is, again, due to the decrease in the number of electrons that are inside the emitter. What is of note, though, is that the Fallon-Rotheim theory, which does not include any of these effects, predicts an ever-increasing emitter current density, which that's a major discrepancy that the two models really point out. Next is the more practical consideration, and that's the consideration in which I have an electronic device with a field emitter inside it. What happens if I replace it with a smaller one and keep the anode voltage fixed? And it turns out that in metals, this still increases the emitter current density. Even though you can see that there are some drops in the current density, overall kind of just continues to increase. So for experimentalists and device designers who are using metal emitters, keep making them smaller, it should work. And the last thing in this section is the Fallon-Rotheim plots. So to explain a little bit about how these work or why they're useful, Fallon-Rotheim has a very simple form. And essentially the major parts are this f squared and this -1 over f. And if the field emission data is plotted on a set of axes where the y-axis is defined by j or f squared and take the natural log, this term is what remains, this -b over f. And this is the equation that you obtain. If this is plotted against 1 over f, however, this should form a straight line. That's just the Fallon-Rotheim result in dash y. And the slope is equal to minus b, and b is a known constant, and the work function to the 3/2. So experimentalists use this to first verify if something's field emission, so they want to see if this is straight, and second, figure out what the work function of the material is. However, as you can see in my model, as emitters get smaller, this becomes increasingly nonlinear. And this is a problem for extracting parameters. So the actual value used in the model is 4.5 for the work function. For a 1 nanometer emitter, the predicted value, which I had to find out what is the most linear part of this, which is already a tough task, but predicts 12.3. So the extracted parameter values are extremely far off from what Fallon-Rotheim. And it does get better as emitters get larger, as the surface gets planar. And if I were to increase the emitter radius to 20 or 30, I'm assuming that it would eventually converge to 4.5 as the surface becomes more planar. But why does this happen? And it's a purely electrostatic result. Fallon-Rotheim plots are linear because the barrier is perfectly triangular, which is shown by this dashed line here. In more realistic models, the barrier is not perfectly triangular, but still essentially triangular. And this leads to a tunneling probability that is equal to this exponential of -1 over v naught. And the tunneling probability in this plot is basically the area between this gray line and the triangular barrier. However, as can be seen, this solid blue line is the paraboloidal emitter potential. And there's a huge discrepancy between the area under that curve and the area under the Nordheim curve. And it's obviously not triangular, and the barrier shape changes very drastically with peak count. As you can see, if you look at the higher voltages, such as 15 and 25 volts, P is greater for smaller emitters. And the reason for this is that smaller emitters have higher field enhancement factors. So a particular applied voltage produces a higher electric field at the surface of a smaller emitter. And as can be seen for the lower voltages show the greatest discrepancy between the Fallon-Nordheim model and the paraboloidal model. And since these emitters are operating at low voltages, the transmission probability is not proportional to E to the -1 over V naught, and this leads to the extreme non-linearities in the plots. So Fallon-Nordheim plots for these small emitters, at least for metals, may not be the most reliable tool for extracting material parameters. And just to recap, it's a one-dimensional system. Most of the current comes from states that don't have any angular momentum. The emitted current density will continue in metals to increase as a function of decrease in radius. And the barrier shape of the Fallon-Nordheim barrier shape for paraboloidal emitters makes it maybe less useful to use Fallon-Nordheim plots for parameter extraction. And before I want to move on from this point, there's another group that's shown that this paraboloidal emitter that has kind of a convex potential, it's not particular to that shape. It's general to all highly curved emitter shapes. So this result should extend into other emitter and anode geometries, not just that paraboloidal one. Next, I'm going to leave metals and enter semiconductors, where the most major distinction is that semiconductors have a much lower current, they have a much lower electron density. So the number of electrons that are available to tunnel is going to play an important role in this. And to look at where this first step towards the semiconductor, or particularly silicon model, comes in, is it's still bulk and it's still planar, but I've changed material from metal to silicon. Silicon is a technologically relevant material, and the goal of field emission research at the moment is to provide high-density, small current sources, and particularly in nanoelectronic devices like the transistor I mentioned earlier. But the fact is, like I mentioned, metals have higher electron densities, and therefore they emit larger current densities. But the major drawback to metals is they lack compatibility with complementary metal oxide semiconductor processing technology. And the significance of that is CMOS technology is what essentially all consumer electronics are made from these days. And not having the support of that fabrication technology is a major hindrance to finding commercial applicability. And silicon has this in addition to being an extremely well-studied and understood and developed technology from the electronics industry over the last 60 years or so. And here are examples of some emitter arrays from a previous segment. So now we know why silicon, but why model it if people have already done it? And the answer is Stratton's model is very simple and it's incomplete. And for me, most importantly, it ignores the effects of quantum confinement, which is what I'm interested in. And while Medinus, about 30 years later, wrote a book about this, the theory is quite complete. It's a compendium of all the things that you may want to consider when you're designing models for field emitters and semiconductors. But again, it ignores quantum confinement, and it's just really hard to use. There's no path between the physics and actually implementing it. And a lot of the things in there are kind of like, just kind of guess. There's adjustable parameters. And so I didn't want to start there. So my goal was to do something in the middle. I wanted to incorporate quantum confinement near the surface and all the major effects that need to be included in semiconductors, including what I call flux-limited emission. And that's just that as the emitted current density is calculated, you need to make sure that there are enough electrons that are coming to the surface to be able to be emitted. And most of these models omit that. And from an experimental side, this was also from a previous group member who was doing a thesis on silicon field emitters. The Fallon-Nordheim plots, as we saw in the middle, should form a straight line. Experimentally shown, this has two straight lines in some kind of region in the middle. And although Stratton theory predicts a single straight line, this does not predict this effect. And later work by Baskin did a numerical modeling of field emission from the conduction band only and showed that the emitted current will saturate because of the limited supply of electrons. However, no one's developed a model that predicts both of these things. So that was also the goal of this. Why to kind of redo silicon modeling. And before the model, I'd like to show how are semiconductors different from metals. Why is this a harder problem? First thing is, I mentioned earlier that metals have enough electrons to screen the electric field at the surface. Semiconductors don't, so the bands actually bend downwards or upwards depending on the direction of the field at the surface because there aren't enough electrons to stop the field from penetrating into the semiconductor. This actually leads to the formation of an area where electrons are confined to a nanoscale region between the surface of the emitter and this forbidden energy gap where no states intrinsically occur. And this is a major point that I'm including in the model as these bound states, which haven't been modeled in field emission. One more minor note that I won't talk about too much. This downward band bending actually increases the barrier tunneling width for electrons coming from the valence band, which is this region down here. Essentially just because this is an area where no states exist and electrons have energies here, they have to tunnel a bit further, which also hasn't been modeled in field emission. Additionally, the band structure of semiconductors is a bit more complicated. For example, silicon has 6 equivalent conduction values in the conduction band with different effective masses. Because of the forbidden energy gap in the middle, there are 2 reservoirs of electrons from which field emission can occur: the valence band, which is essentially metallic, and the conduction band, which is the region that has very few, at least compared to metals, very few electrons available for tunneling. And just a quick diagram of where these things come from. So conduction band extended states are higher in energy, and they are states that are essentially free electrons, and they exist throughout the material. The bound states are localized to the surface of the emitter, and the valence band extended states, like the conduction band extended states, extend throughout the emitter, and their energies are lower and are mostly filled, so it's essentially metallic band. Again, what do I expect to see, or what do I want to know? How does the inclusion of bound states affect the model, since this hasn't been seen before? And how significantly does the inclusion of such states compare to the traditional sources of field emission that are typically included, such as extended states in the valence band and conduction band? So what is the relative contributions from those states? How do dopant density and type affect the emitted current density? So the p-type and n-type emitters show different characteristics. And what is the effect of having only so many electrons available to tunnel on the emitted current? First thing to look at is the emitted current density from each of the regimes in the diagram I showed previously of the conduction band bound states and extended states, as well as the valence band extended states. And the first thing to notice is that the conduction band current is shown in blue. The triangles are the ones that is the contribution from the bound states. So these are the ones that are stuck near the surface. And across all fields, and for both n-type and p-type, this bound state current dominates the traditionally modeled extended state current. So the first conclusion is that it's important to include these, at least from a modeling perspective. Second, the conduction band current saturates in both cases. It happens in high fields for n-type emitters, relatively low fields for p-type emitters, and this is affected the fact that we've just run out of electrons. There are being so many electrons emitted that there aren't enough being able to be resupplied from further from the surface, and this causes a saturation effect. And after this current saturates, the valence band current, which is in the red, is dominant component. So summing all of these current components together into a total emitted current density and seeing what happens as a function of dopant type and density, we obtain this plot. So the circles are the n-type emitters and the triangles are the p-type emitters. And trend-wise, they're pretty much identical. Changing the dopant density changes a few features, such as the fields at which the total current saturates in p-type emitters and to what current it saturates. And this is a result of higher dopant densities in p-type emitters, corresponding to the blue down here, leads to fewer electrons and more holes. So fewer electrons mean that the conduction band current saturates earlier. And above this saturation region is a valence band region where valence band current density dominates. And to see a similar effect but at higher fields and N-type emitters where the saturation occurs at very high fields, below that conduction band current dominates. And just for reference, this is kind of the general range over which these field emitters are investigated. So in the case of the N-type emitters, this may not be, at least according to this model, experimentally observable because of breakdown and tip damage and things like that. And so on to the Fallon-Nordheim plots. The first thing to notice is the experimental results that show this strange flat region between two linear regions is reproduced by this model. And so I call this the transition region. It's the point at which the conduction band current is saturated, but the valence band current hasn't really taken off yet. And below that is where the conduction band current dominates, and above that is the valence band current dominated region. And for the N-type emitters on the left, so this is for P-type, this does happen, but again at very high fields, and it's not very evident if this happens at all. So taking one of the Fallon-Nordheim plots for each emitter type, for particularly dopant density, shows two distinct linear regions separated by some kind of intermediate region. And there's a modification to the Fallon-Nordheim analysis, Fallon-Nordheim plot analysis that you can see in the bottom left of the left plot. And instead of the work function, it's the more general barrier height. So this is just the height of the barrier that electrons that are tunneling see as they approach the barrier. And the reason it's generalized in this case is because electrons in the conduction band and electrons in the valence band see different barrier heights because of where they're located in energy, with the conduction band electrons being much higher in energy than the valence band. So the smaller slope corresponds to a smaller tunneling barrier height, which corresponds to emission from the conduction band. And the larger barrier height in the larger slope region at higher fields corresponds to valence band emission. And so the major takeaway from the model is that valence band emission, which we're not really sure if it can be observed. This model predicts that what was shown in the experimental results actually is valence band. And to recap, the conduction band current density is mostly from the bound states. The conduction band flux density saturates, causing the valence band emitted current density to dominate. Increasing dopant density in N-type emitters provides more electrons, so the saturation current is higher and happens at higher fields. The opposite is true in P-type emitters. And Fallon-Nordheim plots have two distinct regions corresponding to, at least in this model, emission from the valence band and emission from the conduction band. And you can tell based on how the relative slopes. Finally, I wanted to push the bulk silicon model further and model something a little bit more realistic, which was a nanowire. And this is just a step on the way to a realistic model that I'll discuss at the end, but this incorporates quantum confinement effects into the bulk silicon model. And again, on our map of current state of field emission theory, the only Fallon-Nordheim assumption that it retains is a planar emitting surface. And so it's a low-dimensional silicon emitter. Why silicon nanowires? Well, the major reason is that I showed earlier that the dimensions of real emitter tips are small enough that quantum confinement probably should be modeled. And the bulk emitter model really ignores this. So primarily a modeling consideration. But also, as I mentioned earlier, that the saturation region in N-type emitters, according to the model, actually occurs above the observable experimental range. However, Ding, previous group member who did this work experimentally, showed that this happens in the observable range in N-type emitters. So there's a discrepancy between my model and the experimental results. And both of these things point towards, if I confine the emitter, there are fewer electrons, and this region should shift down into the visible experimental range because of having fewer electrons. So the basic physics is still the bulk silicon model, except that the emitter is confined to a NS-scale cylinder. It has a planar emitting surface, so we're not dealing with any curvature effects here. And the major modification is the transverse energies, so energies of electrons and momentums of electrons that are not moving in the tunneling direction are actually now discrete. Formerly, they were continuous. So this leads to a one-dimensional electron system. So electrons moving in this direction have continuous energy and momentum, and ones that have momentum going transverse to emission, are discrete, except for near the surface. So as you recall, band bending causes electrons with momentum moving towards the emitting surface to be discrete. Now they're also discrete in the other two dimensions. So the surface becomes a quantum dot area of 0 dimensions. So the first thing I wanted to do is look at what happens to the total emitted current density if the emitter radius is changed. And as can be seen, decreasing the emitter radius causes the saturation of the total current density to occur at lower value than at lower fields. And eventually, all of these converge towards the bulk model. So it's nice to see that the models are consistent with each other, and that as emitters are made larger, I recovered the results from the previous section. The reason for the earlier saturation of current is because the conduction band current saturates earlier. Quantum confinement reduces the electron density in the emitter, as I discussed earlier, which means that there are fewer electrons able to be emitted, and that this happens at lower fields. This causes the current saturation to happen earlier, and for the valence band to dominate a little bit earlier. And looking at Fallon-Nordheim plots as a function of emitter radius, generally the transition region shifts to lower fields. And so since the Fallon-Nordheim plots are 1 over f, lower fields correspond to a larger x value. So as can be seen in the p-type emitter, the transition region shifts to lower currents and to lower fields. And as can be seen in the n-type emitter, it's a kink in this plot in the visible region, whereas all of the other ones are essentially still linear. So this is encouraging for the model that the n-type emitter transition region kind of transitions to lower applied fields. So maybe this will match the model or the experimental results. And that's what I originally wanted to see with this nanowire emitter thing, is how does this stack up against experimental results? So the first thing to notice is that the structure of a typical single gated field emitter is of a sharp emitter tip, and it is coplanar with this gate. And it's not visible on this, but this gate is actually a circular coplanar. So the tip is in the middle of the circle. And then the metal that forms the edges of the circle applies the field to extract electrons, and then the anode, which is far away, collects them. I don't have the ability to model this analytically, which I need for tunneling calculations. So I tried to do the next best thing was to use the paraboloidal emitter model for the electrostatics. So the electron system itself is, I looked at the papers, I saw what the reported emitter radius was, and I used the nanowire of that radius to model the quantum confinement effects. The emission model, as opposed to the metal paraboloid, is one-dimensional in this case. And so I just used the electrostatic field enhancement factor to convert the applied field for a planar to what it would be at the tip of a paraboloid. So this is just a very rough electrostatics approximation because this needs to be numerically modeled. And in my calculation setup, I need an expression that can be written down. So we'll see how it does. So the first thing is the IV curves for emitters from Steve Carrero's work. And what he did was he made many different array sizes, measured the current versus voltage characteristics, and then divided by the number of tips and plotted all of these on the same axes and got some pretty good uniformity. And so the red dots are my model and the blue lines are Stratton's model, so the first model. And so the major feature here is that my model saturates, it's hard to see in the actual IV characteristics, but they do saturate, they kind of turn over at the top. But mine saturates more drastically and much more thoroughly, whereas the Stratton model does not have any saturation. So it's essentially a straight line in the Fallon-Nordheim plot. And this saturation is very evident in the Fallon-Nordheim plots here. And again, it's hard to see because there's so much data on here, but these experimental curves actually do experience a decrease in slope, and then at high fields, they recover a higher slope. So like a less drastic version of what's seen in Ding's work. And the result of this is the algorithm I use to calculate the saturation effect is very abrupt. It's a hard limit. It doesn't actually consider current flowing in the emitter, which is a more realistic and gradual way of doing things. And I'll discuss the effects of that later. But I believe that with the improvement of that model, this the correspondence between these two results.
What's plotted on the right again?
Oh, what is on the plot on the right? This is the Fallon-Wertheim plot for this data. And this was also experimentally recorded. So these are the Fallon-Wertheim plots.
Okay. Yeah.
And so next I wanted to look at experimental results from Ding's data, who was the one who originally reported these three linear regions, two linear regions and an intermediate region. And I have to make a comment again about the electrostatics model being very approximate in my case. Normally, at least from a theory perspective, Fallon-Wertheim plots are plotted as current density versus field. In an actual experimental setup, these aren't things that you necessarily know. You have applied voltage and current. These are the measurable quantities. So the Fallon-Wertheim equation can be adjusted for this by converting the voltage into a field by this field factor, theta, and by converting the current density into a current by an emission area. And the problem with this, comparing models to experimental data, is experimentalists don't know what the field is, and it's up to people doing modeling to predict a good field factor. So the slope in this case of the Fallon-Wertheim plots, unfortunately for my case, includes this field factor, which is dependent on the geometry of the emitter. However, I can still compare by taking the ratio of the upper region and lower region slopes, because factor should stay approximately constant, which isn't necessarily true, but it is an approximation. It should be able to take the slope ratios and determine what the ratio of the barrier heights are. And I have here this reference ratio. Basically, this is the ratio of the barrier height seen by valence band electrons in the absence of field penetration, which is the energy gap plus the electron affinity of silicon divided by the barrier in the conduction band, which is about the electron affinity of silicon, and it should be about 1.4. So looking at my results and the experimental results, they're both comparable, this ratio, although the actual slopes are quite different because of the mismatch being electrostatics. And so it's reasonable, at least from this set of results, which is for an N-type emitter and a relatively large radius, that this could be evidence of valence band emission. And the reason this is important is because there have been other alternative, not necessarily models, but reasonings for this, and one of them is impact ionization. So it's not been proven that this is valence band emission by any means, so this is support for it. So then I looked at another set of data for P-type emitters, where this was more pronounced on the model, and did the same thing, and compared to the reference ratio. And again, they're both rather close, within 10% of the actual values, or the reference value. So again, more support for this actually being valence band and conduction band emission that are observable experimentally. And the last thing is there are pretty significant limitations to the model. The first was that because of the limitations of the simulation platform I was using, I was limited to a one-dimensional electrostatics model. And what this means is that I assume that the potential in the emitter is the same everywhere, unless you go deeper into the emitter surface. So in that case, this is actually a valid one-dimensional approximation where these lines are straight. However, I did an actual simulation of the nanowire, and you can see that the potential changes as a function of distance from the center of the emitter. So this is already not a good approximation because this changes the bound states in the surface, and it also will change the tunneling barrier due to field penetration. Another major drawback is the lack of self-consistent modeling current equations included. The results that I showed for silicon have a self-consistent Poisson-Schrödinger equation, so the potential and the bound states are calculated together, but there's no consideration of current flowing. Instead, I just count how many electrons are available to tunnel, and if the emitted current density exceeds that, then the electron density able to tunnel goes to zero, and the emitted current density is capped. So what is more likely to happen is that as the electron emitter emits more, there are fewer electrons at the surface, and the electron density actually starts to level off as a depletion layer forms, and eventually all of the electrons that get to the surface are immediately emitted, and leads to this decrease on the left plot of the electron density. And the effect on the emitted current density is a more gradual onset of these saturation effects over a wider range of fields, so less abrupt. And finally, I've omitted surface state emission. It's debatable whether or not this is important, but it's certainly required for completeness. And surface states are probably very important at low fields, which is not the range at which most field emitters are operated at. But they are important for the total energy distribution of electrons, which is important, not necessarily for the total energy above, or the total emitted current, but for how to deal with electrons, I suppose in lensing situations where the energy of the electrons is important. And so finally, in summary, I would consider my most major contribution in the semi-classical framework of field emission, because first of all, it's a fundamental understanding of what field emission is without any major assumptions to start with. And it unifies all the existing regimes of field emission theory, and it keeps in with the same types of physics used in Fowler-Nordheim, but it's more complete. It also serves, as I've shown, as a theoretical scaffolding for developing field emitter models of any dimensionality, material, or geometry, and this is useful going forward. As I mentioned, I think at the nanoscale, field emitter models need to be developed for what you're actually using, not just a general model that you can try to apply to everything. And this serves as a way to derive those models. And lastly, it establishes tools for analyzing, designing, and optimizing such field emitters. So it hopefully will play a role in design, as the models that are able to be developed can be optimized for size versus dopant density and things like that in particular application. And for the nanoscale emitters themselves, dimensionality and geometry are extremely critical. Reducing the emitter dimension changes both the electrostatics and the electron supply. In the case of metal emitters, where there's a very large supply of electrons, the electrostatic field enhancement is what governs the emitted current density. And increasing the field will continue to increase the emitted current density. The opposite is true in semiconductors, which have a severely limited electron supply in comparison, and the electron supply is what limits the emitted current density. And finally, as I mentioned, I think emitter-specific models are absolutely necessary at the nanoscale. So these things need to be looked at in depth. And for suggested future work, I would like to see, this is not my work, someone do a model of an emitter of a very highly curved emitter and a planar anode. This is probably more relevant to device designs, as often there is at least in terms of the length scales, the tip is highly curved, but the anode is essentially flat. I don't really expect this to change too much in terms of the electron supply side of things, since the emitter shape is essentially the same. It's a hyperboloid instead of a paraboloid, but it might change things electrostatically. And the ultimate goal is a low-dimensional, highly curved silicon emitter model. So this is the real emitter model I was talking about that lies outside of all of those circles that I showed earlier. And this is a tough problem because it requires a three-dimensional treatment of electrostatics that's continuous outside and inside the emitter. So the whole domain needs to be simulated. Because the presence of field penetration determines the size and the shape of the quantum well from which the majority of the conduction band current is emitted. And the fact that the field penetrates into the semiconductor means that the magnitude of the field at the surface is also dependent upon what happens inside the silicon. Someone needs to include current equations. And this is also pretty challenging because solving 3 partial differential equations in a 3-dimensional domain takes some time. And so someone will have to come up with something clever to be able to do this on a scale that's needed for field emitters. And lastly, again, for completeness and anything emission from surface states, they are an important part of the physics of semiconductors and metals, so they should be included. And particularly in semiconductors, because they typically occupy the area where there are no states in the band gap. So before I wrap up, I'd like to thank some people. First and foremost, Professor Akinwande, for letting me kind of go my own way with my work, and to allow me to make the decision not to go into the clean room. The project was kind of something that just kind of fell into my hands, and we kept going with it, and we got some good feedback from the community. So it was not what I planned to do. I'm glad that he supported me throughout it, and that it turned up some good results in the end. It was good for both of us, I think. And I hear that a master's student's going to be doing that hyperboloid emitter thing, so I'm glad to see my work might live on. And also my committee members for their feedback. I had 3 committee meetings, which seems probably most people like a lot. but it really guided how my research went forward and the things that I should keep in mind. And it really helped me to understand kind of what's important outside of my own head in terms of what's going on here. And I'd also like to thank the Aquande group, many of you are here, also previous members, for the enlightening conversations at the library, and also just for the daily conversations and the assistance, especially as when I was younger, Melissa and Steve helped me out a lot to figure out what was going on, and thank them as well. And also to my friends here in Cambridge, this is a picture from the first week of orientation. And some of these people are here. I'm not sure why you're not in this picture, Joel. You were here this day, right? You may have taken this picture. So yeah, I think we've all come quite a long way since then. The 3-time game IM softball champions, bringing home championship every year. That was a lot of fun. I look forward to that every year, even though we never won the summer. And the lads. So it's a group of very close friends. Because of Dan is here right now. We had a band over the last year, and sadly, a few of us have had to move away, but the spirit is still there. We had a lot of good times playing together. And also, obviously, my family, my mom and dad are here. My brother is watching online, I believe. And I'd like to thank them for their support and always reminding me to come home, and home is where I feel most comfortable. And this is still my close family, but it's a picture of almost everyone, including my Aunt Pam's family, who's also here, and cousin Dan, and my Uncle John, very close to me. And larger extended family, which is from Hickory Fest. This is the annual Bluegrass Festival that is the highlight of my year. It says family and friends. It's a celebration of North Central Pennsylvania culture, music. Yeah, this is probably the picture I have of the most people in my life right now. So it's a lot of close friends and family members. And also my girlfriend Samia for supporting me over the last year and keeping me in my head and keeping me sane and clear-headed and always reminding me that the next adventure is just around the corner. Thank you for her support. And finally, for my older brother Sonny as well. He's been in the family just about as long as I have. He appeared 3 months after I was born, and he's about 33 years old. So he's been around as long as all of my other family members have. So every time I go home, he provides some good input and insight. It's always willing to spend time with me. So with that, I'd like to thanks for listening, and open it for questions, I suppose.
Time for some questions. Should we direct the first question to the older brother?
Yeah. I was asked if he was going to be watching. I don't know.
Yes, I'm curious about the silicon wall. So you said most of the current comes out of these states. Do you have any requirements from it?
I did not include band-to-band tunneling for that. I think it's a consideration because one of the questions that people have asked is, so I showed the plots of the 3 linear regions, it's probable that valence band emission or states from the valence band play a very important role. And one of the opportunities for that to happen, besides coming directly from the valence band, is tunneling into the surface states and things like that. So I didn't include it, but it's another thing that I'm aware of that that could be a way that the valence band actually interacts with emission. Because there's a camp of people out there who think that, or claim that valence band does not really engage in tunneling at all, because the barrier height is too high. But that is certainly a channel that I would consider modeling, but I did not model it.
So for the small metal parabolic model, you have this nonlinear Fowler and Nordheim.
Right.
Are there any experiments that observe or that preclude emitters being selected?
So I think actual Fowler Nordheim plots are rarely completely linear, and I think that's for a variety of reasons. But I think most of them are electrostatics based. But for that particular nonlinearity of that magnitude, I don't think I've seen that. And maybe the reason is I'm mostly used to looking at semiconductor data. So I would expect that to be less pronounced in semiconductors because the change in the field also depends upon penetration in semiconductors. So since the field is less repelled, the barrier shape isn't as extremely curved in semiconductors, at least what I expect. But yeah, so I haven't observed that in metals, but generally photon plots aren't linear. So they just pick the most linear part and they just back from there. And they do exhibit a downward curve as far as I understand. But yeah, like that quality or that.
All right, so let's do Alex and we're now going to transition into the committee alone. Having the Thesis Defense. If you can, please wait outside. And, Alex will be able to join. Well,
That's all, folks.
Hard to say.